Alright, the first problem from last weekly contest, maximum unique subarray sum after deletion. We are given an integer array nums and we are told that we can delete any number of elements from nums without making it empty. After performing the deletions, select a subarray of nums such that all the elements are unique in that subarray, and we are maximizing the sum of that subarray and returning that maximum sum. Right? So straightforward. Since we need to maximize the sum and there is no condition on which elements we need to delete, so we will always delete negative numbers if there is, and always consider all the positive or zero. Even zero is fine, right? But there is one edge case that we need to take care of. What if all the elements are negative? Since we cannot delete the elements down to empty, we have to select the largest negative number that we can, right? So we can prepare ourselves in the first iteration itself, and we can have a flag to see if all the elements are negative. In that case, we can just return the smallest or the largest negative number that we have tracked off in the first iteration itself. And the next thing is all the elements in the subarray must be unique, so we can use a set in that case. So we can have a set, we can have a all negative check, which will be a flag initially 0. We can have a answer, and we can, since we need to keep track of the largest negative number or actually the smallest negative number, we can do that by having this. This will be initially, actually, since we are talking about negative numbers and we want the largest negative number, we can initialize it with int minimum. And first thing we will check if n is less than 0 or it is a number which has already been encountered. In that case, we will continue. Otherwise, all negative check must be over now, so it needs to be turned 1. Answer can be incremented and the set can have this element so that we don't encounter it again. The next thing is the smallest negative number can be updated always before we are continuing to the next element, so we can have a max on this depending on the new element encountered. If the flag is still 0, in that case I can return the smallest negative number, otherwise I can return the answer, and that's it. Let's see if this works. It does. Let's submit it. This will be O of n, space will be O of n, since we have a set, right? Moving to the second question, closest equal element queries. So we are given a circular array nums, this is important, and the array queries. So for each query I, we have to do the following: the minimum distance between the element at index queries of I and any other index j in the circular array where nums of j is equal to the nums of that query of I as the index. If no such element exists, answer of that query should be -1. So we need to return the same array size of answer as we have queries. And yeah, so since this is a circular array, there will be wrapping arounds. So let's take this example and let's see what is it saying. Right, so if I have this as the index and this as the query, in that case I'm here, I'm going to check the next one that is closest to this. Why not have a map or something of 1 with all of its indexes, right? That can help us. 0, 2, 4. Similarly, for 2 as the key, 1, that's it. 3 as the key, 4, that's it, since this is the only, actually 5, my bad. 5. For 2 it will be 6, not 1. For 1 it will be 0, 2 and 4. For 4 it's going to be 3, and for 5 it's going to be, there is no 5, and that's it, 3. So 0, for 3 it's going to be 1 and 5, so 0, 1, 2, 3, 4, 5, 6. Alright, so all of them, we can have something like this. This can help us because at a index I want to calculate the next closest one, right? It can be this, it can be this, it has to be this, because 1, 2 with 2 jumps, 1, 2 with 2 jumps we reach next one. There is another way, that is 1 jump, 2 jump, 3 jump. This will be another one. This will be basically a wrap down around version of it. But since the minimum is required, so we will have 2 as the answer, and that is it. We have a 2. For the next thing is 3 at third index. At third index, yeah, at third index we have a 4. Since we don't have another 4, we return -1. That's not possible. For 3, that is, for 5, that is the third value. So the next 3 is, there is only one 3. So that will be 1, 2, either this distance, 1, 2, 3, 4, or the wrapped around distance, 1, 2. So 2 is the answer. Actually, not 2. This 1, 2, 3. So 3 is the answer. 3 is the answer. So straightforward in terms of simulation. This kind of structure, if we have a storage of this sort, it helps. But we are still going to have to, do a O of n or O of m if m is the length of the queries, and for every m, or for every query, we are basically doing a search on this vector of values that we have and minimizing our distance among them. That is not right, since that will take our m complexity to be n into m, which will be uh, you know which will give us TLE. So we need something better. Do we need to calculate or minimize our distance among all the indexes that we have as the value? No. What we can do is we can have the index. We have the index as we go through the query, right? So the queries will give us the index. What we can do is we can search that index, that indexes index on this vector of indexes. So if 0 is the index that we get, in that case I will search for 1 as the key, right? I'll get the vector. In this vector I'll search for 0. Where is 0 lying? It'll give us an index of that particular index in the vector, so that will be 0 in this case. So 0, 1, 2, right? Right. So 0, 1, 2, 0 will be what we are having. Suppose it was 1 instead of 0, right? Just to give some clarity on all the cases. So in that case we are going to check the previous element, right? Suppose there was some example like 0, 1, 2, 3, 4, 5 and 4, 2, 0, 1, 3, 5, something like this. These are the indexes, these are the indexes of the indexes, right? So in that case, if we get something like a 0 or this is as the index, now we are going to search the one before 2. So 2 minus 0 will be one distance, 1 minus 0 will be another distance, and for covering all the cases, we can also check for the extreme versions as well, and that's it, right? That's all we are going to do. So as I code it up, it might be more clearer. Since we are doing a binary search, that will be, that will help us to bring down the time complexity by a lot, right? So what we can do is we can create the structure first, which will be a key as int and the value as vector of int, which will show the indexes. So this is the index map, or let me, yeah, index map is fine. Since I need an index, so let's enumerate over this. Alright, so index map will be basically nums of I dot push back I, right? So this is the structure that we wanted. So let's have a vector of int as answer, right? For every index that we get from the queries, we are going to, you know, create or or find the distance for this query. Let it be int max initially, since we need to minimize it. If we can't, if it still stays int max after the complete, after the loop or after the iteration for this particular query, and it still remains int max, in that case we can have -1, right? So now we want to search this index's position inside this vector, right? So what we can do is we can do a binary search on this, since all the vector of indexes will be in sorted order by default. So what we can do is we can do a lower bound or upper bound search, which will, since all the element will always be present in the vector of int, right? So it's not going to give us any edge case scenarios. This will be a dot begin. Similarly, a dot end, and lastly I'm searching for what, the index, and since I want the index not the iterator, let's subtract it with this, and this will give us the position of the index in the vector of int or the indexes. So I will check one index before, the next case is check one index after. By check I mean minimize the distance, and then next two case will be extreme cases, extreme left check and lastly extreme right check. Alright, so let's get the before index, which will be mp of index -1. If the before index is greater than equal to 0, only then we can do the minimization, which will be basically minimizing distance among what. So among the absolute difference between index minus index map. So since this is a before index, so I will subtract index first, but it doesn't matter since we have an absolute value here. We can do it either way. So basically we are going to have before index. So this will give us the index and this is the index of the current element. So we are minimizing here. We can do the same thing for the after index. This time it will be +1. This time the check will be that it should be less than the index map, or let me, it should be less than this size, and if it is, in that case I can minimize it based on after index this time, and that's it. Right now the extreme case will be, the left extreme check will be a minimization on the extreme left, right? So basically if we have a vector of int, right, like this, in that case, since this will be uh, in the sorted order. So by the way, this should be in sorted order. I made a mistake here. This is it. Suppose this is the vector of index. This should be in sorted order. The extreme left will be the beginning of the vector, right? So what I can do is first check if the index map, just to be safe here, nums of index dot size, or should not be empty, right? And index map of nums of index dot 0 will be the first element. If it's not equal to index, that means this is not the same element that we are talking about, or it is the same element but it is not the same index element or the same copy of the element that we are talking about. So in that case we are going to minimize it among distance, among so there will be two things that we are going to consider here. Since it's a circular array, the one way to reach point 1 and 2 will be this difference. The other way to reach point 1 and 2 will be this. This distance and this distance will have some value. So this is the difference, or the absolute difference, the normal way that we calculate, basically index 1 minus index 2, the absolute difference of index 1 minus index 2. This, on the other hand, this circular array basically has a circumference of nums dot size. I'm sorry, this handwriting is too bad. Let me write in short form, size. This is what size is, and this value will be basically size minus difference, right? So we are minimizing among these two differences, so that will be, let me calculate the difference first so that I can reuse this variable. So absolute value of nums dot size minus or let me get the difference first. So that will be basically this, absolute difference of this minus index, right? Similarly, I get the difference here and nums dot size minus difference, right? Since this is basically iterator, so I need to typecast it to integer, and I guess we are good. We are good with this. We are going to do the same thing for the right check. This time it shouldn't be empty, and instead of 0 it should be the back of the vector, right? So let's copy this and update this as well, and the remaining will remain the same, right? That's it. So I can update my answer, so I'll push it to the answer this distance, but before pushing I'll check if it's equal to int max. If it is, then -1, otherwise distance. I can return the answer here, and let's hope for the best. If this works, there might be some. Okay, this seems to work. Let's submit it. Okay, this does work. Time complexity wise, let's see. So this is going to basically be a O of n if n is the number of number size, and this will be O of m, and for every O of m we are doing a lower bound search on a vector of int that could be as large as n, so it will be a log n search for O of m log n. And I guess these are just one operation, O of 1. So this is it. I guess m log n is the time complexity, and the space complexity will be again suppose all the elements are distinct, so in that case it can be I guess m into n, if I'm not wrong, in terms of space as well. Alright, so this is the second problem. Third problem, zero array transformation 4. We are given an integer array nums of length n and a 2D integer array queries, where queries of I is of the format LIRI value I. For each query, we are going to select a subset of indices in this range and decrement the value at each index, right? So basically, we need to do this to ultimately achieve zero array. That is all the elements in the array must be equal to 0, and we need to do such that we return minimum possible. Okay, so there are there are n queries, right? There are queries, query 1, query 2, query 3, query 4, query 5. So these are queries, not the format that query is, but this is the count of the queries. Suppose at this point I'm able to make all the elements 0, right? By the time I reach here. So in that case, I've used 3 queries and 3 will be my answer, right? And if we can't do that, even if after using all the queries, in that case, return -1, right? So what we are basically doing is, in terms of operation, we are selecting a subset of indices in this range and decrementing it by exactly value of I, right? So there can be scenarios where the value nums of I is greater than value of I, it can be less than value of I, it can be equal to value of I, right? If it's equal, then good enough. I don't worry about this element again. In the further queries, I won't select this whenever it is lying in the range. If it is less than value of I, in that case, I can't use this, right? Because I can't make it negative because there is no way to increase it. So, cannot use it here. If it's greater than value of I, in that case, I can use it. But if I use it and I'm able to make it some new value which I am never able to reduce it, right? So in that case, that won't be valid. So I may or may not use it here. I may or may not use it depending on what's the future, right? So here, if I write it, may or may not use, cannot use, definitely use, right? So this is it. This is the basic gist of this question. So now there is two ways to look at it in terms of perspective. The one way is the linear way of looking at it and doing it for every query, right? For every query, we are updating the numbers array and doing the thing, but that will lead us to TLE. What we can do is we can basically do it for every value inside the numbers array. So for every value inside the numbers array, we are going to do all the queries, right? In terms of doing all the queries, I mean use all the queries to the point where the value becomes 0. So it will be giving us an index, and that will be true for all the values of numbers array, because we are going to do that for all the values of the numbers array. So all of them will give us indexes. I am going to use the maximum index, right? I'm going to use the maximum index, and that will be our minimum possible k, right? Why I'm using the maximum index? Because the maximum index is the one that is going to decide when the entire values of the numbers array is going to be 0, right? That's why that's our answer. So that's how we are going to solve this. So for that, let's code it up. Initially the value will be 0. Let's get the nums.size as well. So for every element, we are going to do the operation, right? And what that operation is, we have already discussed about it, right? So for every value, we are going to do this. This is a DP. So we are going to create a DP function. But before that, if the value of the element is already 0, in that case, I don't have to do anything. I can continue, right? So I'm going to get an index. Let's call it sub answer. Okay. So that will be basically based on a DP called, let me call it solve. We are going to pass the value that we are going to reduce, right? We are going to pass the queries range. So let's pass the queries itself. We are going to pass the index of the numbers array, because we are going to check if we can update this value or not based on this query. If we can't, we can't, right? So for that we need the index. we are going to pass the 0th index. So for queries, this index, for nums of I, this index, right? And lastly, that's it. That's all we need. So let's do this solve function first. So we are getting a num value. We are getting the queries. So vector of int. We are getting the nums index. We are getting the index of the queries. So first we are going to check if the nums or num value is already 0. In that case we can return what? The index of the query where we are at. So we'll pass the return the index itself. If we have crossed the line of the index, that means this particular value can never be 0 even if we use all the queries in all the query inside queries. So in that case we need to return something that's going to indicate here that it is not possible. So in that case it can return the maximum value. What is going to be the maximum value? Well, the maximum index can be 1001, right? So if I return 1001, I can just check if the sub answer is equal to 1001 here. In that case we can return -1, right? Otherwise we are going to maximize the index and return that, right? So we need the index here for the particular value num to become 0. We want the smallest index, by the way, right? So what I can do is I can have an answer which will be again the maximum that is possible, 1001. We can get the index from the queries. We can get the end index as well. We can get the value as well. So this will be 2, this will be 1, this will be 0. So if the start is less than equal to, if the nums index is falling within range, right? That is, start is less than equal to nums index and nums index is less than equal to end. In that case, I'm going to do the thing, right? But the problem is I can only do the thing if the value is smaller than nums of I or equal to nums of I, right? So what I can do is I can have another check, nums of, or the num as the value. If it's greater than equal to value, only then I can do this thing, that is answer is equal to minimizing the answer that the solve function is going to return. So I'm going to pass the value. Since I'm using it here, I'm going to reduce it by value. I'm going to pass the queries. Nums of index will stay nums of index and index will increment by 1. Now comes the other choice of skipping it, right? I can always skip irrespective of whether it's falling in the range or not. So I can skip it here itself. So I can minimize the answer here as well. Let me copy this. But since I'm not using it here, I won't reduce the value and that's it. That's it. We can return the answer here, and let's see if this works. This works, but we can minimize it. This will give us TLE. So we have this and this, right? Actually, not this. This is basically, never changing. This is changing and this is changing. These are the two states that is changing. So what I can do is I can have a cache of these two things, vector of int, vector of int cache. This will be of size nums of I plus 1 because the value is the state, so it's sized this way. The next thing is vector of int the size or the index of the query as the state. So it's going to be queries.size plus 1. Initially -1 as the value. We are going to pass the cache. So let's add it as a parameter. We are going to check if cache of num and index is not equal to -1. In that case, we can return it here, right? And let's not forget to pass the cache. Let's see if this works. It does. Let's submit it. Time complexity wise, it's going to be O of n here. So for every O of n, we are doing a DP of this. So it's going to be max value of the numbers array as the state into the query's size, that is suppose m. So let me write down the time complexity. That will be O of n into max element of nums into m, that's the index of the queries. We can do better, by the way, and that is doing some sort of binary search here, but I guess this is it. This also works. Alright, so this is the third problem. Fourth problem will be count beautiful numbers. So we are given two positive integers L and R, and a positive integer called beautiful. The definition is that if the product of its digit is divisible by the sum of its digit, in that case this is beautiful. We need to return the count of all the beautiful numbers between L and R, inclusive, right? So we have 10 and 20. In this case only 10 and 20 are valid. Why? Because there is a 0, and whenever there is a 0 involved, it's going to be valid because the product is going to be 0, and the whatever the sum value, that doesn't matter since it's always going to be divisible. Here we have 1, 2, 3, all of them, since the product of a single digit is the digit itself and the sum as well, so it's always divisible. And since the values are very large, this straight away indicates towards digit DP. So basically what we can do is we can calculate all the numbers till L minus 1, right? Since it's inclusive in terms of L and R, that's why I took L minus 1, and calculate all the numbers till R, right? And if we subtract these two values, we will get the ones in between, that is L and R, L to R. So that's the first thing we are going to do. But how we are going to calculate till a certain point all the beautiful numbers, right? So we can do DP. DP will have some states. States will be, first thing is product, that is obvious. Second thing is sum, that is also obvious. Third thing is uh, third thing is index. Fourth thing is going to be something that requires a little bit of explanation. So we want till a certain point. So we have a upper bound and we don't want to cross that. Suppose the number or the upper bound is something like 7, 5, 6, 9, right? 8. Or let's give a 0 as well in between, right? So if this is the upper bound and we are generating the numbers that are below this, right? Let's forget about beautiful numbers right now. We want to just generate numbers using digit DP, right? So what we can do is we can create positionings, right? So at this position, I need to place something. If I place a 0, it's fine, but I have placed a 0. That means I have made sure that any value that I use forward after this 0 is going to be smaller. It's always going to be smaller. This number is always going to be smaller than this number, right? So I can use any number after that. 1 to 9, 1 to 9, 1 to 9, 0 to 9 actually, right? But if I would have selected 1, in that case, that's also the same thing. And that's true for 2, 3, 4, 5, 6. But if we select 7, in that case, there is a upper bound. I can't select more than 5 right now. Right? I can't select 6 here. But if I select 4 here, in that case, I lose that tight bound and I can allow myself to select anything between 0 to 9 after this, right? So that's something that needs to be required in our state. Let me call it is tight. Is tight means I have a upper bound. If it's a false, then I don't have a upper bound, right? The last thing as a state is needed, or sometimes it may not be needed, depends on the approach. I am going to use the fourth state and I'll call it if it is having a leading 0 or not. Has leading 0 or not, right? So has leading 0. Why is it required? Well, it's required because product and has leading 0 needs to have some relation, because if I have some upper bound as 64, right, 63, right, in that case if I create a number using DP as 01, right, in this case this 0 doesn't really mean anything. If we don't have any has leading 0 as a state, in that case we are going to consider our product to be 0, but that shouldn't be the case. So if has leading 0 is 1, product is always going to be 1, or at least greater than equal to 1. It's not going to be 0 even if we encounter 0, because has leading 0 is means that all the elements till now is 0, right? As soon as we encounter some element, we are going to make this a false. In that case, if we encounter a 0, then it's going to be a 0. We don't have a choice, right? So that's it. We are going to solve this problem By the way, there are few assumptions here, and that assumption is basically all the numbers between 0 to 189. If we do a product on these numbers, then we get certain, a limit on the numbers that we can get, right? I mean, there is a upper limit here which I don't have a proof for, but I've read about it in the solution section, in other solution sections, that they have a limit of 4,000 as the limit on the distinct products that we can get between these numbers, right? In terms of, for every number, all the, you know digits product is what we are talking about. It's only going to be 4,000 in terms of distinct products, right? So one, or let's take an example: 12, 13, 14, right, and so on and so forth, is going to give us 2, 3, 4 as products, right? So if we do that for all of them, we are going to get 4,000 distinct products if we do it for all the numbers between 0 to 189. And the same is true for sum. So let me copy this down. It's going to be 100 in this case. Digit sum, digit product. So this is an assumption that helps us, come up with this approach. But regardless, it's not going to be used here, since we are going to memorize it, but not using these values. I'm going to create a key for that. So before that, let's solve this problem. Let's have a sub answer 1, which will be calculating the values or beautiful numbers count below, or till L minus 1, right? So let's have a solve function that's going to calculate it. I will use a string for it, so I will convert it to string. It makes things a lot easier, since we are, anyways, using positions to indicate a digit. If we have it in string format, that's going to help. So the index will be 0 initially, the product will be 1 initially, the sum will be 0 initially, and lastly, uh, the is tight bound is going to be 1. We are going to start it as 1 and not 0, right? So this is L minus 1, this is index, product, sum, is tight boundedness, and has leading 0. Currently we are having a leading 0, so it's going to be true, right? So we are going to do the same thing for the other one as well. This time it will be R, and we are going to return sub answer 2 minus sub answer 1, right? So this solve function is going to take string, the index, the product, the sum, the is tight boundedness, and has leading 0. If the index, that's the base case, if the index is exhausted, right? So in that case, I can return what? I can return 0 or 1 depending on the product and some divisibility, right? So product mod sum is equal to 0, right? But there might be scenarios where sum is equal to 0. In that case, I need to have a check that sum is not equal to 0, so that there won't be any invalid case of dividing it by 0, right? So first thing first, I'm going to use numbers. What numbers I'm going to use depends on if the is tight boundedness is true or false. So I am going to have a digit upper limit based on the digit limit. So this digit limit is going to be so let me call it digit here. So the first thing is get the digit from the string of number in integer format, and this is going to help get the upper boundedness based on is tight value. If it is 1, then my digit is going to be the upper limit, otherwise 9 is going to be the upper limit, right? And I'm going to count the beautiful numbers in my answer variable. I'm going to either choose 0 till the upper bound as the digit. If I is equal to 0, there will be a certain case, otherwise there will be another certain case. Why? Because if I is equal to 0, I am going to have a product value and has leading 0 relation, right? That's going to be useful here. So this stays as it is. This will be incremented. So this stays as it is. This is incremented. The product, right? Since I is equal to 0, product value is decided based on has leading 0. If has leading 0 is true, in that case product will be 1, right? In that case product will be 1 because has leading is 0. That means any 0 encountered is not a valid 0. So product stays 1. That means if has leading is 0, it's going to have a true value. So that's going to be considered as 1. Sum will be staying as it is because I'm not incrementing anything. I can also do plus I, doesn't mean anything. The next thing is tight, right? So is tight stays true or false depends on whatever I value we have selected, right? So digit limit, if the selected digit I is equal to the digit limit, in that case my is tight boundedness is going to change accordingly, right? It's going to stay true. But what if I have broken the digit limit boundedness once and then I am selecting this again? In that case, it shouldn't be true, it should be false, after that throughout, depending, irrespective of whatever I select I as. So that means I'm going to have a is tighted boundedness, ended with this condition, right? This can be confusing, but it shouldn't be, right? The next thing is has leading 0 will stay as is, right? The next thing is this condition. Here we are selecting some I which is not 0, so this should be 0 now. and product I should be a valid value here, and sum should be incremented by I, and that's it. We can return the answer here, and let's see if this works. After that we will memoize it. So there is some mistake here. To underscore string. So let's not pass it by reference in that case. Okay, num str, not nums str. Okay, what's the issue here? Digit limit. Oh, so this should be digit, not digit limit. Alright, let's now memoize it. So we will have a lot of states, right? This will be technically till 4000, this will be technically till 100, this will be 2, this will be 2, this will be of size uh, the size of the string, and that's it. I mean, in terms of the maximum size we can have, it should be 11 or 10, I guess. Depends on the value of R. And lastly, uh, yeah, I guess these are the states. So what I can do is I can create a key and use a string to integer value as my cache. So map will contain a string comma integer as cache, and I can create a key here using the states. That key will be basically index, stringed version of index with a delimiter which I can choose anything, product, uh, let's copy this. Alright, so index, product, sum is tight. I guess index, product, sum is tight, has leading 0, and that's it. Great. So I guess this is it. Here I can have a check if cache dot find key is not equal to cache dot end. In that case I can return cache of key and update it here as well, and let's see if this works. Actually I need to update clear the key here when I'm calling it for the second time, so let's clear it. Let's see if this works. Let's submit it. And this works. That's the fourth problem. Thanks.